Hello and welcome to today's webinar, Wastewater, Tackling Production Capacity, Environmental Compliance, and Operating Costs, sponsored by Evoqua. I'm Joyce Vassell, Editor-in-Chief of ProFood World. Food and beverage manufacturers are striving to optimize production while achieving high levels of quality and compliance. With a more adventurous consumer and the growing foodie revolution, consumers are taking a deeper dive into the ingredients and processes that create their favorite dishes. Having efficient, safe, and sustainable processes is key to making a good impression on the informed consumer. Today, food processors are faced with rising utility costs and increasing wastewater disposal surcharges, along with the desire for a smaller environmental footprint that will yield a sustainable operation. In today's webinar, you will learn details on proven wastewater solutions that enable growth and expansion, how to achieve ROI on your on-site wastewater investment, benefits in water reuse and energy recovery, strategies for dealing with evolving compliance requirements, outsourcing services for wastewater treatment needs, and a real-world example of how to meet changing consumer demands for innovation and sustainability. Before I introduce our speakers, I want to let our audience members know that this webinar will be available for archived viewing at profoodworld.com. You will receive notification when it's ready, and the slides will be available for download from there as well. Please feel free to ask questions at any time during the webinar by typing your question into the questions pane of the GoToWebinar control panel, and we will take some time at the end of the presentation to address some frequently asked questions as time allows. So let's get started by introducing our speakers. Bill Cole is Wastewater Treatment Advisor at Evoqua, and he has more than 25 years of engineering consulting experience providing sustainable water and wastewater solutions for the food and beverage industry. Bill has been on the forefront of the latest technologies, compliance, and process modifications for byproduct recovery, water reuse, and labor-saving applications. Evoqua's process engineering manager, Daniel Bertoldo, has 10-plus years of experience in the process design, commissioning, startup, and aftercare of biological wastewater treatment systems for the food processing industry. And Daniel has also played an active role in the organization's R&D efforts, where he co-authored and presented multiple papers. So now I'd like to turn it over to our first speaker, Bill Cole, to begin the presentation.
Thank you, Joyce, and thank you everyone for joining us today. I hope you didn't have to travel very far to get to this webinar. Over the course of this presentation, we're going to try to offer you some thoughts on evaluating wastewater treatment options and finish with the aforementioned case study for New Belgium Brewing. We're going to presume that you have a basic understanding of wastewater treatment, and for those of you that have more than a basic understanding, please forgive the oversimplifications that we're using for the illustrations today. We're going to be discussing wastewater technologies only at a very high level. The intent of the presentation is to give you some concepts and some ideas on how to select what's best for you in your situation. Just briefly, I'm assuming that most people on the call understand this terminology, but here's just a little reminder, some of the acronyms that we're going to be utilizing today. So wastewater, I think most people are aware that it has these following impacts. Unfortunately, it's not the favorite topic for investment purposes in a facility, and that's understandable. You want to invest money in the production side of things, not the wastewater side of things. Often it's only dealt with after it needed to be, so you're already struggling with the wastewater treatment issues if it's an existing system especially. So we're going to give you some thoughts on how to basically evaluate costs when looking at a new system or an existing system, how to extract whatever savings you can from the treatment systems and become a hero, take the savings, turn it into a bonus for you. Now, with wastewater treatment plants and food processing facilities, there's a variety of interesting challenges. The production changes, there's CIP cycles, there's unknown spills and chemical additions when something is changed in ingredients or sanitization chemicals, and of course, getting funding to make any improvements is a challenge as well. We're going to try to help you with some of these things. So when you're evaluating options, basically you've got a new installation or you've got existing installations. We're going to try to address both of these, but which one you have makes a difference in how you look at it. Obviously, a new installation, you can do things right the first time. Existing installations, you may be constrained by what equipment you already have or what the site conditions are. There may not be space, etc. In addition to that, there's a growing emphasis on operations as well, making the operations as efficient as possible as far as byproducts, waste, energy, labor requirements, things of that nature. So we'll talk a little bit about automation and a little bit on outsourcing some functions that may be specialty, so you don't have to know everything about your wastewater treatment system, just enough to keep it running each day. So design considerations are going to take into account things like where are you discharging to? Is this water going to a municipal wastewater sewer? Is it going to a surface water discharge? How much room do you have? Is this going to be a facility that has the potential to grow in the future? What kind of product change-ups are you going to have? And of course, it comes down to money as well. What money do you have available? What labor do you have available? That's increasingly tight. Are there some considerations where you might be able to outsource some or all of the operations and the capital equipment? Where we start with all of that is trying to recognize what are all the costs that are going to be associated with the water and or wastewater treatment system. So on that front, the more data that we can collect before we start evaluating wastewater treatment systems, the more informed and better choices that you're going to have. So things like a mass balance throughout the facility, wastewater analytical data, obviously. Operational costs at the various steps where you're modifying the water, impacting the water in some way. And you're not expected to know how to do all of that or where to look. So there's a lot of help outside available to you in the form of consulting engineering firms. Equipment solution vendors can do this, a lot of this as well for you, and sometimes they're teamed up with the consultants to help provide you the data and the information you're going to need to justify what's best for your facility. So when we look inside the plant, many of you will recognize that water is everywhere. But everywhere there's water, there's also a cost associated with this. Anything from adding heat energy and chemicals at the boiler treatment steps, or the cooling towers, also a chemical treatment, and there's a lot of wastewater that comes out of a cooling tower, things of that nature. Also the lab. So if you look in more detail within your facility and start blocking off the major water users, the major destinations for the water, the uses of the water, the ultimate disposition of the water, and the byproducts of the water, this is a good template to utilize to say, okay, these are the areas that we need to at least take into consideration for what's the cost of my water at each of these steps, and where are there water reuse opportunities. It might be point source water reuse. For example, we could take the cooling tower water, blow down, treat it, send it back to the cooling tower again, and avoid having it go to a wastewater treatment plant, ultimately shrinking the size of the wastewater treatment plant. Why would you want to send cooling tower water to a wastewater treatment plant if you could avoid it? That takes a lot of volume out and potentially a lot of cost. So when you're looking at the cost, just to reiterate, look at all of the aspects of the water coming in, the water going out, not just what the meter says on the front end and what the meter sewer bill is on the back end, but add in the other costs, including labor associated with these various steps. And this will give you a comprehensive picture when you're justifying the type of wastewater treatment system you're going to use. We keep talking about the type of wastewater treatment system, but in reality, there's a large number of technologies that can go into a water and or wastewater treatment system. Unfortunately, or fortunately, most of them will work to get you to where you need to be. There isn't one solution, unfortunately, that fits everybody. It's a little easier on the front end process water side, but on the back end, on the wastewater side, there's so many different variables that have to be taken into account in the constituents in the water, and the temperature of the water, the fluctuations of the water flow, et cetera, that there just isn't one size fits all. So since there isn't one size fits all, we're going to try to give you some examples on how to compare the various options to make the best choice for yourself. And it won't be the same for every industry even. It's really site specific, it's client specific. So we're going to talk about some of these technologies, but we're not going to go into detail on any of them. This isn't about how these technologies work. It's more of, here's some different examples of what would work in a given situation and how we compare which one is potentially best for you. So I'm going to break these down into real basics. All those other technologies that were on the previous slide can generally go into these four categories. There's physical processes, which are things like screens or dissolved air flotation, media filters, membranes, things that are basically physically taking out solids out of the water typically. The biological side of it is taking out the dissolved organics that the physical processes don't really impact. So essentially, this gets digested by microbes. We're going to get into that in a little bit more detail, and that's going to be the focus of a lot of the rest of our discussion here. The chemical side, almost every aspect of the wastewater treatment is going to have some chemistry associated with it, whether we're adjusting pH or doing coagulation or doing sterilization on the back end. So you can't avoid having the chemical impact on any of these. Thermal is a bit more on the extreme side. This is basically boiling off the water to eliminate it. So we're concentrating it into a liquid form, or we could take it all the way to solids. Generally not applicable in food and beverage, so we're not going to focus on that, but I just want to make you aware that it is there. So if we go back to where the different technologies may fit and how to categorize them, we could take a look at this as a primary treatment step, a secondary treatment step, and a tertiary. So the primary is where we're going to be filtering out solids, if we just keep it that simple. The secondary side is where we're going to take it a bit further, and we're going to digest or eliminate dissolved organics for the most part. On the tertiary side, this is where we're polishing it up. We're either polishing it up for discharge, for reuse, maybe some other beneficial side use, but it's a polishing step. We're not going to spend a lot of time on this today either. We're going to focus on the secondary part, the heart of this, because that's where the biggest impact is financially, footprint, every other aspect of the wastewater treatment plant. Most of the heart of that's going to be the secondary side. So that's what we're going to focus on today. If we took those different technologies and we put them into a chart that showed where they applied relative to the strength of the wastewater we're going to be treating, and how clean we need to get that wastewater, we could, in general, plug the different technologies into something that looks like this, with the high-strength wastewater in the upper left-hand corner where the anaerobic tends to thrive. And as we go down and to the right, where the cleaner water is, we've got more aerobic or membrane-based systems. And in between there, you'll see that the dissolved air flotation has a spot as well. And you'll see why in just a moment. I'm going to talk about primary treatment step. This is going to be part of almost any other process that has the secondary or the tertiary. But often a primary treatment step can be all you need for your wastewater treatment needs if you're going to a city discharge. So primary treatment, taking out suspended solids, but it also takes out biological oxygen demand, organics that are associated with the solid portion of what you're removing. So if we look at the process flow diagram here, you'll see that the active components are primarily a screen, take out big chunks of things, sticks, gloves, stones, and a dissolved air flotation system, which essentially uses air in combination with chemistry to float out smaller suspended solids or oil and grease that simple screening systems aren't going to catch. So if you look at this particular example, you'll see a high level of suspended solids that were reduced by 98%. That's the TSS. The oil and grease was also reduced by 98%. And as a result, the biological oxygen demand was reduced by 80%. So we're down to 900 from starting at near 5,000 milligrams per liter. In this particular case, this was enough to meet city discharge requirements and, maybe more importantly, save a tremendous amount of surcharges that the city would have been impacting this particular facility with if they had been sending raw wastewater to the drain. So these types of systems typically have a pretty good payback. So if you're not executing something like this now, this is probably the best thing to take an initial look at. These can have a return on investment as short as a year and usually within 2 or 3 years. Fairly simple to operate. If we need to go an additional step, we've got our primary that we just looked at in that red circle on the top. We're now following it with a secondary treatment that allows us to polish this up to either below the surcharge levels for discharge to a city, or now make it suitable for surface water discharge, or in this case, it's going for irrigation water. But we could add a tertiary step to this as well and turn it into something near potable water or boiler water feed, quality, cooling tower, things of that nature. These 2 steps would be the workhorse for almost any wastewater treatment process for the food and beverage industry. We're going to focus on the secondary for the remainder of this presentation, since that's where most of the money and most of everything is being spent and utilized. So I'm going to talk a little bit about 2 basic types of secondary treatment on the biological side. We've got the aerobic, which, as its name implies, uses air. And essentially, we are taking aerobic microbes, giving them food and air in some type of a tankage. We've got them contained. And what they're doing as a result is they're consuming the soluble organics and turning it into sludge and turning it into carbon dioxide. The other approach is anaerobic. Anaerobic doesn't require air, and as a result, it doesn't require as much power. And as another consequence of anaerobic technology, it also produces a lot less sludge, and it produces a beneficial biogas. It's beneficial if you can reuse it in boilers or produce electricity or a number of other uses we won't get into at this time. But the reason I bring these up is we're going to compare these in a couple of examples coming up here on how to decide what's best for you. So if we look at the aerobic side on the left, you'll see that for 100 kilograms of COD, we're using 100 kilowatts of aeration. Half of what comes in goes out as sludge. You'll see that we're getting about a 90 to 98% reduction in the COD, so fairly clean water. On the anaerobic side on the right, we're not using power for all intents and purposes. There's a little bit of pumping cost, but there's no air being injected, a whole lot less sludge being generated, so that's a benefit. But if you look at the reduction in the COD strength, we're getting about 80 to 90%, so not as much as the aerobic. Often an anaerobic will be used in front of an aerobic system to get the combined benefit of both, and we'll be talking about that a little bit later. So let's look at those aerobic solutions again. Those of you that are familiar know that there are dozens and dozens of variations of these out there in the marketplace. We're going to focus on a few of the popular ones here, by popular meaning more common. A conventional activated sludge system on the left is very similar to what you'd see at a lot of municipalities. It's basically a big tank, followed by a clarifier, and inside that tank we're blowing a lot of air to give oxygen to the bugs that are consuming the food, and then we're using a clarifier to capture the bugs that are escaping and send them back into the swimming pool so they can keep eating. We take a few of those bugs off every once in a while, usually on a continuous process. In this case, dewater them and throw them away as sludge. A variation of that especially for industrial applications these days, is something called a moving bed bioreactor. It's basically a fixed film. It just means that we're now pouring places to live for those microbes into the same type of tank as the conventional activated sludge. So think of honeycomb cereal being poured into a big tank, and now biofilm can form on those surface areas, allowing a much denser population of aerobic microbes. And the benefit for an industrial application is now we can make this more compact. And we don't have to send the bugs back from the clarifier back into the swimming pool because they're already hanging on that fixed film media. We still need some type of clarifier or dissolved air flotation at the end, and we'll see that in upcoming block diagrams, just to capture the dead bugs, because we don't want them going down to the next step in the process, whether it's going to the sewer or tertiary polishing. And then another variation of this is just to put a membrane where the clarifier or the DAF would be. So now you've got that open swimming pool concept, but instead of a clarifier or a DAF, you've got a membrane that's holding all the bugs in. And as a consequence, we can keep more bugs in a smaller space. So like the MBBR, this is also a smaller footprint than the conventional activated sludge. A little bit more expensive because of the membranes, but you get better quality water that might be more suitable for reuse, and we're going to talk about that in a little bit. On the anaerobic side, again, an oversimplification. We've got high rate anaerobic, and what that means is that the water retention in that system is a very short period of time, usually just a few hours. Consequently, it's a very small footprint. It has to have the water very conditioned in order for this to work, meaning we can't send it high solids, oil and grease, things of that nature. We need to control the operating parameters within a very narrow range. So it's not very forgiving, but it's very compact. And if you don't have space, that might be your only choice. If you do have space, a medium rate reactor where the water retention time is longer can handle higher solids, higher FOG. It's more forgiving, a little bit easier on the operation, but we have to have something to catch the solids like the conventional activated sludge and send them back into the process. The low rate system takes a larger footprint because it has a higher retention time, but it's the most forgiving of the three. It can operate in the broadest range of any of those anaerobic technologies, including taking high fat, oil and grease, high suspended solids. It often can be the only step in the process, not requiring any pre-treatment, not requiring any post-treatment like a DAF. So we're going to talk about that a little bit further. So if we go back to the primary expansion or primary treatment that we talked about before, that a lot of existing facilities may already have, especially for a city discharge that included the screen and a DAF and the oversimplification here. Often what will happen is you've increased capacity at the plant or production. You're no longer meeting the city requirements, or the surcharges have increased, or the limits have dropped. So what can we do? The good news is you can add one of those processes, in this case an aerobic MBBR, the moving bed bioreactor, followed by a DAF, certainly meet the city discharge limits. It might be a new phosphorus limit that they've imposed for you, or they've lowered the level at where they're going to start charging surcharges, or they're just asking you to reduce because they need additional capacity within their facility. So they're asking the industries to do further pre-treatment. This is a relatively simple add-on. These are typically modular, so you can expand them in the future. An easy choice. If you wanted to take that concept a bit further and reuse some of that water that you're now cleaning up, we could further polish that water with an additional membrane bioreactor, followed by the DAF that we had in the previous example, but at this time now start sanitizing it with some ozone, use some media filtration or a membrane to further clean the water, and then use it for reuse. Could be boilers, cooling towers are a commonplace, truck washes, things of that nature. Another example of that would be to utilize the membrane system, the membrane bioreactor. This allows you to utilize the water directly to an RO, for example, which would be very suitable for almost any use within the facility. Now let's take a look at those three on a comparison chart, just in some very basic aspects: their footprint, the amount of sludge they produce, and the energy required to operate each of them. There's certainly a lot of other factors to consider, but if we just kept to these three for illustrative purposes, you can see the total area in yellow above there that the MBBR, in this case, the moving bed bioreactor, actually has the smallest footprint. Okay, big plus for that. The membrane bioreactor comes in next. The conventional activated sludge is always going to be the largest because, again, remember, it's that big swimming pool followed by a big clarifier to catch the bugs and send them back. So we need a lot of room. The second thing we're looking at here is how much sludge is being generated. The amount of sludge generated is going to translate directly into a cost because obviously that sludge is going to have to go somewhere. Typically it gets dewatered, and to the extent of dewatering really depends on what the disposition of the sludge. Is it going to be land applied? Is it going to go to a landfill? Are you going to incinerate it? Those are all factors that add some variation into what might be best for you. And then, of course, the power consumption. You can see that in this case, the MBBR came out a little less than the conventional activated sludge on the right. The membrane bioreactor has more, there's more pumping involved in a membrane bioreactor, and there's some scrubbing involved. That involves input of a blower typically. Also, when you just compare the footprint on a very simplistic basis like this is what it looks like visually. So in this case, this particular client was looking at initially putting in a conventional activated sludge. Until they did the comparison, they ended up putting in the moving bed bioreactor. They might have gone with the membrane bioreactor had they had an advantage for water reuse, but in this case, they did not. So let's look at another real-life example that might be relative to some of you. There's a client that has a 70,000 gallon per day discharge going to a city. They've got an influent to whatever the treatment plant would be of about 1,500 ppm of suspended solids. The city is going to require 300 ppm. The influent BOD is 6,000. The city is requiring 500. In this particular case, the city wasn't giving them a choice. It wasn't that, I'll keep discharging and we'll just charge you surcharges. The city is a smaller municipality. They needed the capacity, so they didn't have to invest in expansion themselves. So they're going up the pipe to this particular industry and asking them to do some additional pretreatment. So they too looked at three particular options for meeting those discharge requirements. So here's the familiar moving bed bioreactor in a little more detail than the overly simplistic one we looked at earlier. So we've got an EQ tank. We've got the reactor tank, a 55,000 gallon tank you see in the middle. Then we've got the dissolved air flotation to collect the sludge, and none of that has to be recirculated back to the MBBR. It's one of the advantages of that. And then we're dewatering that sludge, and I don't remember what the disposition was, but you could see in the chart in the lower left-hand corner that this is where the performance is coming in with this particular technology. And we're going to compare that now to one of the other technologies. In this case, it's a sequencing batch reactor. Sequencing batch reactor is very similar to the conventional activated sludge, except it's happening in batch form instead of a continuous form. So when we look at this technology, we would compare it with a conventional activated sludge. Much larger tank, similar performance. And then we also compared anaerobic in this case. And the anaerobic system you can see is much simpler of the three, but it requires a 700,000 gallon tank. In this case, the client had the room for it, so they took it into consideration. Performance characteristics not quite as good as the aerobic, but in this case, good enough for what the city is requiring. The other thing, of course, to take a look at is the footprint of these three technologies, and we can see here that the footprint, you can't read the small print, but trust me, the footprints are relatively the same. The anaerobic in the upper left-hand corner is basically a tank. The batch aerobic is several tanks and a DAF. We need some equalization in this case. The same with the MBBR over on the right. more importantly, we looked at the operational costs in this case. So presuming that the operator attention is the same for each of these on that upper column, or that upper row, sorry, we looked at the electrical requirements, the chemical requirements, and the sludge production to give them, again, an overly simplistic operating cost, not taking everything into account, but taking just the basics. So if we take a look at the anaerobic in this case, which is what this particular facility selected, their electrical requirements that we've highlighted in yellow here came in far less than the two adjacent ones. You know, we don't have the blowers, so we don't have that electrical cost. And we look at the chemical requirements because we don't have the dissolved air flotation, and in this case we don't have as much pH adjust requirement. The chemical cost came in quite a bit lower for this particular case as well. So if we add in the reduced sludge production that we saw in the slide illustrating the anaerobic sludge production, this particular case came in more than $100,000 less than the SBR on an annual basis, and a couple $100,000 less than the MBBR. There's other cost considerations that go into this, and with the capital costs being roughly the same between these three, in this particular case, this customer installed an anaerobic system. Now, the anaerobic system isn't going to win out in every case, but in this particular one, the benefits that this particular client saw was a lot less sludge, a lot less power. They're going to utilize the biogas for their boilers, so they're getting a CO2 offset, and they're getting the value of the saved natural gas. They also liked the fact that it was a very stable process with a large turndown capability. They have outages and they have product mix changes. An anaerobic system can be turned off for weeks at a time. An aerobic system has to be continually fed even during outages. So while we're talking on the anaerobic technology, it's also being more and more commonly used to increase the capacity of an existing conventional activated sludge. So if you already have an aerobic system, not just a conventional activated sludge, but any type of aerobic system, and it's reached its capacity, or it needs to handle more future capacity, or it needs to reach tighter surcharge limits, or you just want to reduce the amount of sludge being produced and lower your operating costs, an anaerobic can be a good add-on solution. This can be added in front of the activated sludge system to then reduce the load on the activated sludge system and consequentially the operating costs in terms of 80 or 90%. So 80 or 90% less sludge, potentially 80% less power, et cetera, et cetera. Another opportunity to upgrade an existing activated sludge system is to turn it into a ballasted system. I'm not going to discuss the technology here so much as to make you aware that if you have a system now that's overloaded or nearing that, or you need to get better quality water out of it, or your clarifier keeps puking up sludge because it's getting overloaded, you can add on a relatively small technology that doesn't increase your footprint, but it can double the capacity of an existing system, and it can more than double the quality of the water coming out as well. Just another thing to consider with whoever you're dealing with that's going to help you review your wastewater treatment system. And then finally, just kind of wrapping up here, once you've cleaned the water to a certain degree with a secondary system, you can add a tertiary treatment and take the water to whatever level of reuse that you might want or discharge that you may want. And that this is just one example of several ways to do that. So just wrapping up, what we would encourage you to do, first and foremost, is collect as much data as you can, and trending data as well. You know, anything that you can get over the course of days, weeks, months is helpful to whoever's going to be helping you with the evaluation of your wastewater treatment system. Also, always compare multiple options. Sometimes doing nothing is the best option, but compare as many options as you can afford the time or expertise to do. evaluate the capital and the operating costs. A lot of people get lost in the capital costs and neglect really detailing out the operational costs. Make sure you get operation or process guarantees on whatever you put in. This can be tricky, and it can be, there's a lot of suppliers that could supply you something that might work for a little while, but that ends up not working in the long run for you. So make sure that of your source on your process guarantees. And then we always want you to look at modularity. If you need to expand this thing, how would that look? And maybe build that in up front if you're putting in a new system or expanding an existing system. And then, of course, where are you going to get your service support? That newfangled thing that you bought from Australia, where does the service come from for that if something happens with it? So think about where your service is going to be, how it's going to be serviced, maybe even consider outsourcing some of those services or even in the operations. With that, I'm going to turn this over to Daniel, and he's going to describe a case study with New Belgium Brewery.
All right, thanks very much, Bill, and thanks everyone again for attending this webinar. And I'm pleased to discuss this case study on the on-site wastewater pretreatment system installed for New Belgium Brewery in Asheville, North Carolina. Next slide, please. So New Belgium Brewing Company is one of North America's largest craft brewers, and they pride themselves on producing high-quality beer under environmentally and socially responsible policies. So the success of their brewery in Fort Collins, Colorado, allowed them to expand to a new brewery in Asheville, North Carolina, which has the capacity to produce 500,000 barrels of beer per year. So the company elected to conduct on-site wastewater treatment at the Asheville Brewery in phases. So for phase one, consisted of installing an equalization tank so that the brewery wastewater could be equalized and pH adjusted prior to discharge to the Buncombe County Municipal Treatment Plant. And then as part of phase two, that consisted of installing a biological treatment system to pre-treat the wastewater to significantly reduce the organic load being discharged to the sewer. Next slide, please. So New Belgium is a progressive company, and they spent significant time and resources researching technologies to find which solution would be the best fit for their brand. So in addition to evaluating the pros and cons of various treatment approaches, New Belgium wanted to select a technology which they could be proud of and would adhere to one of their core values and beliefs, which is environmental stewardship, honoring nature at every turn of the business. As part of their selection process, New Belgium identified several challenges with on-site wastewater treatment at the Asheville site. The brewery is in close proximity to a residential neighborhood and walking trail, and the brewery itself serves as a tourist destination. So wastewater treatment plant needed to fit on a very small section of property adjacent to a busy intersection and not produce unacceptable levels of light or odor or noise. Additionally, New Belgium sought a technology which would digest some of their spent hops and yeast to increase biogas production, as waste diversion and biogas utilization aligned with New Belgium's environmental and sustainability policies. Furthermore, New Belgium did not want to just meet the discharge limits. To fully adhere to their core values, they wanted to consistently generate a very high quality final effluent, which far surpassed the treatment requirements. So after taking all of these challenges into consideration, New Belgium determined that anaerobic membrane bioreactor technology would meet their requirements for environmental sustainability, social responsibility, and integration with the local community. The anaerobic MBR process itself pairs anaerobic digestion and membrane filtration into a single treatment stage. So the primary advantage of the anaerobic MBR technology is the ability to provide near perfect solids retention and generate anaerobic effluent free of suspended solids. The membrane barrier retains all the biomass within the system, which ensures efficient treatment and stability even under high organic loading conditions. The physical membrane barrier results in a more reliable method for biomass retention compared to strategies used in alternative anaerobic technologies. So the combination of complete mixed conditions in the biological treatment system, operation at high biomass concentrations, and near perfect retention of solids allows anaerobic MBR technology to strike a very good balance between high biological stability and process efficiency and compact system footprint. The anaerobic MBR system generates the best quality effluent among all commercially available technologies, which aligned with New Belgium's desire to generate effluent which far surpassed the treatment requirements for the municipal discharge. So as shown on the process flow diagram on the screen here, in gray, prior to installing the anaerobic MBR system, wastewater from the New Belgium plant was pre-screened using an externally fed drum screen, and the screen liquid was discharged to an equalization tank. A recirculation loop was used to mix the EQ tank contents and monitor pH, and equalized wastewater was pH neutralized prior to discharge to the Buncombe County Municipal Treatment Plant. So as part of the second phase of the treatment plant, New Belgium selected ADI Systems to design, install, and commission the anaerobic MBR system, which is shown in color on the flow diagram here. As part of the project, modifications to the existing infrastructure were conducted, which included increasing the capacity of the influent lift station pumps, upgrading to a jet mixing system for the EQ tank to increase the mixing intensity in the tank, and upgrading to a larger internally fed rotary drum screen. So wastewater is conditioned with supplemental alkalinity and pumped to the continuously stirred tank reactor, or the CSTR, as part of the system. The anaerobic biomass in the CSTR removes the bulk of the organic load in the brewery wastewater, and a single membrane tank was installed to house the membrane cassettes, which are used for solids liquid separation and biomass retention. And to minimize space requirements for the membrane tank, double-deck membrane cassettes were selected. The permeate extracted from the membrane cassettes is discharged to the municipal treatment plant, and biomass is continuously recirculated from the membrane tank back to the CSTR using the RANS pumps, and a sludge dewatering system was installed to thicken the waste solids prior to off-site disposal, and a stream of biogas is continuously recirculated through the membrane tank to scour the membrane surfaces, and excess biogas generated from the anaerobic MBR system is discharged to an enclosed flare for combustion, with New Belgium's long-term plan to utilize the biogas, thus creating green energy from the brewery waste, which again conforms with their views on environmental sustainability. Next slide, please. So this site photo here highlights how the anaerobic MBR system was installed on a really small area adjacent to some road traffic, meaning the treatment plant had to be designed to meet New Belgium standards for appearance and emissions on noise and odor and light. So the process tanks, equipment, and interconnecting piping, they're all arranged in a somewhat visually pleasing manner, and an enclosed biogas flare was installed to shroud the flame that's generated from burning waste biogas. The CSTR and the membrane tank were covered to prevent odor emissions, and the biogas blowers were equipped with enclosures and silencers to ensure noise emitted from the treatment plant did not exceed max noise levels at the property boundary. Next slide, please. So since system startup, the system has generated exceptional quality effluent. In addition to consistently generating effluent with suspended solids consistently less than 2 milligrams per liter, the anaerobic MBR system has reduced organics measured in terms of chemical oxygen demand, or COD, from an average of 9,000 milligrams per liter in the wastewater to an average of 150 milligrams per liter in the final effluent, and that corresponds to a removal efficiency of greater than 98%. So these consistent removals reinforce that pairing anaerobic digestion and membrane filtration into a single treatment stage can result in a high degree of stable and efficient treatment. Furthermore, the consistent performance also demonstrates how anaerobic MBR technology is a suitable method for breweries to dispose of their spent hops and yeast. So raw brewery wastewater typically has suspended solids concentrations less than 1,000 milligrams per liter. But the addition of spent hops and yeast to the wastewater increased the suspended solids concentration to around 2,600 milligrams per liter. So the spent hops and yeast, they contribute additional loads of organics and solids, which could not be handled in other anaerobic treatment systems that are traditionally installed for breweries. However, the design features of the anaerobic MBR system, namely the long solids retention time, the high biomass inventory, and the complete mixed conditions and perfect solid retention, they all kind of work together to digest these solids and generate additional biogas without compromising on effluent quality. Next slide, please. So the anaerobic MBR system, it needed to meet municipal discharge limits of 220 milligrams per liter, but is actually designed to achieve an effluent BUD of less than 60 milligrams per liter. For nearly all other anaerobic technologies, this level of performance is just not achievable. But as shown in the figure here, the average final effluent BUD is typically around 20 milligrams per liter. So that's much lower than the design final effluent BUD concentration of 60 milligrams per liter, and significantly lower than the discharge limit of 220 milligrams per liter. So by going against historical convention and installing an anaerobic MBR system for on-site wastewater pretreatment, New Belgium have adhered to their core values on environmental stewardship. The level of treatment achieved by the anaerobic MBR system when treating the combination of processed wastewater and spent hops and yeast, it far exceeds the requirements for discharging to the municipality, which aligns with New Belgium's commitment to waste management. The treatment plant does not impact the aesthetics of the surrounding residential area or the brewery, which benefits the local community. And the consistent performance of the anaerobic MBR system in terms of solids destruction, organics removals, and biogas production lays the groundwork for future energy recovery through biogas utilization, which will be conducted in the third phase of the wastewater treatment project. And that concludes the case study on the New Belgium system, and thanks a lot for your attention.
Okay, so now we'd like to take some questions from the audience, gentlemen. The first person says, I thought anaerobic treatment was just for high-strength waste. Bill, can you comment on that?
Sure. Yeah, it's a common understanding that it's, maybe misunderstanding, that you need very high strength waste before you can consider anaerobic, and it's really much more circumstantial than that. There's a wide band of crossover between anaerobic and how far it goes into the aerobic treatment realm. A lot of it depends on the constituents of the water, obviously. So don't rule it out. Anything that you're looking at initially, ask if anaerobic is a consideration and throw it into the mix if you can compare it. There's certainly a lot of advantages to it.
Okay, our next question is actually a two-parter. The person says, operationally, how do the three solutions you discussed compare, and do they all require the same experience to run?
That's a good question. I'm going to tackle the experience part of it first. They're all learnable technologies to operate. So typically you're going to be given an operations manual and hopefully some startup training on these things. And then whomever is supplying the different technologies, whether it's through an EPC, an engineering procurement construct firm, or total equipment solutions vendor like a Evoqua, they're going to provide you ongoing support if something unusual happens, but it's all learnable. But I think the real delineation on operating a wastewater treatment plant is the next level of detail that has to be incorporated in knowledge if you're doing surface water discharge. There's certain rules and regulations that apply there, and pretty serious consequences if something isn't operated properly. For most sewer discharges to a municipality, if something goes wrong, you usually have an excursion that you're going to get fined for. And if if you're doing a water reuse, obviously you're going to require more training and more a higher level skill set to maintain a more complex system. So they're all different, just like the wastewater treatment systems, but it's all ultimately learnable. You don't have to have a particular background necessarily. Next question.
Okay. Next question is, which of the technologies are the most commonly used for new installations?
Boy, I would suggest for new installations, again, it's situational dependent, but just taking a real broad brush, the fixed film technologies like the MBBR, the membrane-based technologies like the moving bed bioreactor, and of course the anaerobic treatment. So comparing the three, as you saw in the previous illustrations, if you need to have water reuse as part of your consideration, you need to conserve the water, bring it back into the plant, maybe meet a high discharge limit. You may want to take a look at a membrane-based system like a membrane bioreactor. That is the more expensive, typically, to take a look at, as you saw in the previous illustrations, both in capital and operating cost. And can be a little bit more on the sophisticated side in operations as well. The moving bed bioreactor, if you just need to meet some fairly relaxed discharge standards to a municipality, can be a good choice. It's a once-through type of system that doesn't require a lot of attention. It has a little higher operating costs than some other choices, but it's a very simple process. And then the anaerobic, of course, if you can qualify your waste stream for anaerobic treatment, it probably does offer you the lowest operating cost. And depending on which type of anaerobic system, it can be the most forgiving and easiest to operate as well. So again, whomever you're working with that is going to be helping you with your wastewater treatment choices, just make sure they have an intimate familiarity with all of the options, not just the three I mentioned, but there's a dozen other ways to do this as well.
Okay, well, I'd like to thank Bill Cole and Daniel Bertoldo from Evoqua for a great presentation today on wastewater, tackling production capacity, environmental compliance, and operating costs. And for the latest news about engineering and operations in food and beverage manufacturing, please visit profoodworld.com. Thank you for attending this presentation, and have a great day.